This talk is going to be about PDE models. One thing I wanted to mention right at the beginning, there's now these core area pages. So this is a page where we have like an overview of the functionality of what we can do in PDE modeling, like geometric modeling, mesh generation. You'll see some pictures there, specific topics, heat transfer, fluid dynamics, and things like that. And I'm going to talk about all of those in a second. Okay, so let's look at PDE models. So PDE models have received quite a few updates for version 14 and quite a few new additions. So for version 14, we've made updates to the heat transfer. The solid mechanics got a few updates, actually quite a few updates. We have new fields of physics, like we started exploring electromagnetics and fluid dynamics. And we also have a new field that's now, I've called the Schrödinger equation or Schrödinger, but we'll discuss that in a second too. It's a bit different from the other ones, but we'll get there as well. Okay, so if I speak about a field of physics, what can you expect in the reference to find there? So typically there is a monograph about a specific field, for example, heat transfer. That is going to explain the equations, derive the equations. It might have application examples. It's going to go through workflows, how to set up your simulation to make these type of simulations. It's going to go through different aspects of modeling heat transfer in this case that I'm talking about. So that's what you're going to find in the monograph. Then there's going to be a guide page. And that guide page usually has some PDE component reference page, like heat transfer PDE component reference page. And there's going to be links to boundary conditions on the boundary condition reference pages. Then we have application models and application examples. So application examples are typically what you'd find in a reference page. So if you go to a heat transfer PDE component, and all the application examples there that you find there are application examples. And some of them are a bit more elaborate or more interesting than others. So for those that are more interesting and more relevant, we've added links to the PDE overview page so that you can quickly find them. Application models is a way more elaborate application example. So this is a possibly complicated application, might be a scientific work, or it might be an engineering type of work that is more involved that it would fit in an application example. So these type of things you can find, and we're going to see a few later in the talk. For some areas, we have verification tests. This is basically to convince you that what we're doing is correct. So there you'll find references to books, papers, analytical solution, and we verify that the stuff we do is correct. So you can have a look at those. So there are PDEs that become very complicated, especially when you couple them with other models like fluid flow and heat transfer and things like that. And then you don't know how to set up these PDEs because they become pretty complicated. So what we thought is useful is to have functions that generate these PDE models. To recap a little bit, what I mean by a PDE operator is, so if we look at this diffusion type of equation or operator here, so we have a divergence, a gradient, a parameter, a coefficient, so to speak, and u and x. So all partial differential equations or all differential equations for that matter that we model always have a dependent variable. In this case, u is the dependent variable, and they always have an independent variable. So x in this case is an independent variable. Sometimes they have a time variable, sometimes they have a frequency variable like omega. Very often they also have material parameters like this kappa here. So these are things that we need to consider when we generate PDE models. We need to be able to address these type of components, so to speak. And here we look at a specific example, like the heat transfer PD component. So the dependent variable is T, the temperature. X, it's a spatial problem, and it's listed again here as the independent variable. There are no parameter specifications for this example. So the way it goes, it's XYZ PD component, variables, and parameters. That's for all of them. It's the same order basically, and this generates this component, this PDE term collection basically. The -1 is the default material parameter for this. T is the dependent variable, and X is the independent variable. In this case, now we have a time-dependent problem. So T enters this part of the specification, and here is another T, and it generates a time-dependent component. And again, in 3D, you just add the XYZ there. Now, again, a time-dependent setup, but now we specify specific parameters like a mass density, specific heat capacity, and the parameters that you can specify are all listed on this heat transfer PD component reference page. So you can look at those. So here you see how these parameters, the thermal conductivity is this coefficient that enters here, the specific heat capacity and the mass density enter here. So that's the way to do it. You can also say, I have a material, in this case, copper, and this is from our entity collection, and then it just takes the material data from this entity, and it adds the actual values into the component. Okay, so while we're talking about heat transfer, there have been quite a few updates. So here you have this update show changes, and if you click it, these updates are going to be shown. And if you scroll down now through the notebook, you'll see, well, yeah, so in yellow now you see these are things that we've added for version 14. The reason we do this is the body of text we have by now is growing fairly large, and we cannot expect people to reread all these monographs from version to version. So that's why we try to make this visible. Make the changes visible with this functionality, basically. Okay, so what have we done? So we've reworked how volume, line, and point and layer heat sources work. We've added a new example for a temperature-dependent heat capacity. So that's a new. I mean, it's a nonlinear example, and if you click on these, you'll get to the actual example in the documentation. So if that's something you're interested in, you can have a look there. So here's a new example for heat transfer in multi-material media, freezing of liquid. That's a second example in this area where we have materials, or water in this case, that has multiple phases. And there's new section on multiphysics heat transfer. Solid mechanics updates. There we've added axis symmetric models. That means if you have an object that has an axis of revolution, you can solve the problem in this 2D or 2.5D plane and then infer the complete 3D solution from this. This is useful when you want to save the time and not compute the entire 3D domain. It's much easier and cheaper to solve this 2.5D type of version. So that's something we've added for version 14. Then we've added transversely isotropic linear elastic materials. That sounds complicated. It's not. So here we have, think about layered structures, for example, rocks and things like that, that have a specific layer order. These type of problems can be solved with transversely isotropic material laws. We've also added non-orthogonal material laws, and that makes things even more complicated. That means that now the material can be arbitrarily oriented so specific points in the material can have specific orientations. It's another level of complexity that allows you to model different materials. And we're going to see a few examples in a minute. We've also added a standard reinforcing material model. That means if you think, for example, about concrete, and that concrete is reinforced with steel, that type of stuff can now be simulated with these new models. Hyperelasticity is the field of physics where we have material that's extremely deformable. Think about rubber. You can pull it forever, almost, and it will go back to its original state. What we've done here is we've added, again, new material models here. Here is a list of the models that we have. So the Muni-Rivlin is new, Arura-Boyce is new, Ghent is new. We have 2 different Neo-Hooken models now. So there's a new collection of material models. We've added nearly incompressible material models. So if you want to do a deformation, a hyperelastic deformation, we've added models that try to preserve the volume of the deformed object. That's what you typically want. We've added sections on model calibration. So typically for people that do hyperelastic material models, they have experimental data and they need to fit their hyperelastic model to this data. This is something we're particularly proud of because it's dead simple now to do this in the Wolfram language in Mathematica, because fitting material data is so easy, and we've made it that these components like fitting the data and the model calibration work very well together. Hyperelastic models are now available for plane strain and plane stress models, multi-material models. So this is maybe another thing to look at. We have a block of different forms of rubber, if you will, and we pull them to the right, and depending on their material properties, they deform differently. So there you see, so this one deforms differently from the green one, and again from the purple one. So that's a way to specify multi-materials that are hyperelastic. We've added functionality for multiphysics coupling, and I'll show an example of that in a second. And again, also hyperelastic transversely isotropic material. So we're going to look at those also in a second. Yeah, we've already talked about this. We have new hyperelastic material models, so people that want to use these can do so. Let me show you a bit more what I'm actually talking about. So this is a material reinforced with fibers. So this material has the fibers reinforced in this direction. We hold this block fixed at the left-hand side and pull it to the right. So now if I change the orientation of the material of the fibers, you see, now they're a little bit at an angle of 30 degrees, and we still pull to the right. You see that the material deforms differently depending on the fibers that we have. And if we change them more, 45 degrees, and change them even more, now 60 degrees. And then again, if they're orthogonal, we have a normally deformed object. So these type of things can be solved with this reinforced fiber material module that we've added. A second thing I wanted to showcase here is that we've made changes and additions so that you can couple hyperelastic materials with other fields of physics. And in the example I'm showing here is we've coupled so this is basically a rubber gasket in a hot environment, a hot and moist environment. And this gasket is deformed and it also absorbs some of the moisture. So let me play this video. I mean, this is just to show you a bit what can be done. So this is a fairly complicated application model, but things like that can be done now. So coupling of hyperelastic materials with mass transport for the moisture and temperature heat transfer is possible. Okay, so here we have a rectangular region. Think again, some kind of a rubber. We're holding it fixed at the left, and we're pulling on the right-hand side in the right and to the right direction. We specify the rectangle, that's the domain. We specify the vars, so it's u and v is displacement in the u direction and in the v direction, and the x and y are the independent variables. We specify the parameters, so we say this is a solid mechanics material model. We want a neo-Hookean model. We specify the shear modulus. The model form is a plane stress case, and the thickness of this thing is 0.01 units. Okay. Now we specify the boundary conditions. It's a solid fixed condition on the left-hand side, x equals 0, and you give the same vars and paths like before. And solid boundary load at this edge here. And we say the force is some value F, and it goes in the right-hand to the right-hand side, in the direction to the right. Load is a function of F. It's this force that we're going to see used just now. So we now make a model, a function of F, this force we've talked about. The solid mechanics PD component vars parse equals to the load of this force that we're going to enter just now. And the boundary condition is the fixed condition. As a quick sidestep, if I were to evaluate solid mechanics PD component on these vars and parse, this is the equation I'd get. And that's the reason why we have these PD components. This is nothing anybody can remember and should remember. So these functions generate these type of equations for you. That's why we have them. Okay, let's continue with the example. So I want to exert a force of 12 to the 12 kilonewton. I have n-dissolved value model, use this force, the dependent variables are u and v, and the region omega. And that's going to give me a displacement. So this is now a visualization of the displacement, and that displacement, that visualization is to scale. So this is rubber, and we've really pulled it quite a bit. Okay, so next I'm going to go ahead and increase that force a bit. So I say, okay, we want 20 kilonewtons. Do the same thing again, the same plot again, and we get a larger displacement. Now I go ahead and I say, I want 40 kilonewtons, and now I get a message that find root failed to converge. So typically what you should do is, if you get such a message, is you should click on this information I. That will bring you to a message reference page, and in that message reference page, you should find an example that addresses this type of a problem. So we have an object that's undeformed, the rectangle, and we want to deform it to a huge deformation, like a huge load is put onto that object. And finite element solvers at some point cannot do this step from the zero deformation to the final deformation in one go. And that's not a problem that problem is not something that's special for us, that every finite element solver has that problem. That's a typical problem. So what we can do, however, is we can do something what is called a solver restart. And for that, we use this force of 40 kilonewtons, and we make a parametric and dissolved function and use the model that we had before, force, and multiply this with a parameter p, and that's the parameter of the parametric and dissolve. So we get a parametric function, the parameter is p, and what we're going to do now is we're going to vary p from 0 to 1 slowly. So we're slowly going to increase the force. Okay, we're going to do this in 10 steps. The maximum value for this scaling is 1. And we start from displacement of 0, so no displacement. We have a do loop here. We compute the first scaling number, so step times 1 over step, so 1/10, the first step. And now we call this parametric function with this variable, so 0.1, and give the initial seeding, so where to start from. U is the displacement 0, and V is the displacement 0 from this previous step. Once this solution is found, displacement is rewritten, and in the second loop, in the next loop, we're going to use the previous versions of that displacement. So we slowly iterate our way up to the full a force of 40 kilonewton. And then we can do even these large displacements for a larger force. So this is a common problem for highly nonlinear problems, that the solver gets stuck and we'll have to do a solver restart. And the basic idea is to solve it in small steps and incrementally push the solver forward to the correct solution. So now we change gears a bit. There is one new addition from the finite element functions that I'd like to show. We have a new, in the ND-solve finite element context, a new function that's called discontinuous interpolating function. And there's a reference page for it, and there's some additional documentation. So interpolating functions have problems when the function itself is discontinuous. And they also have problems when derivatives are discontinuous. So that's something that this discontinuous interpolating function tries to tackle. And to show you what I mean is I've generated a mesh with two different regions, like the gray region and the white region here. And what we're going to do now is we are going to write a function. And if we are in this one region, we have the value of 0. And if we're in this other region, we have a value of 1. So there's a steep interface between these two regions. So now I want to evaluate that function on this mesh. And what we do is we use the function evaluate on element mesh. And in this first step, I'm going to show you the legacy output. So if you say discontinuous interpolation goes to false, then you get the normal interpolation function like we've used in previous versions. Now, if you look at the min-max of the values that it's generated, you'll see there's over and undershoot, and it's even more clear in this plot that we have a little bit of a overshoot and undershoot. So if you now evaluate that function with evaluate on mesh, you'll get a discontinuous interpolating function. And the way evaluate on mesh knows whether to use this discontinuous interpolating function is basically it looks at the mesh and has a look if that mesh has several material regions, and then it does this discontinuous interpolating function. If we now look at the min-max of this discontinuous interpolating function, we'll see it's 0 and 1 exactly, and the plot is very crisp at this interface. So maybe some additional information is this works basically by storing interpolating functions for the subregions, and it has a very clever algorithm to decide which subregion it needs to look at to get the proper interpolating function. So here's a plot through a cross-section, so at 1/2. Again, here it's very sharp, the interface. And now we're going to look at these points at the interface specifically. So in this case, we evaluate at the interface, and it has the value of 1. That's what this discontinuous interpolating function returns. So if we have two materials, epsilon1, epsilon2, this point, or generally this edge, it's not clear where this edge should belong to. Should this belong to epsilon1 or epsilon2? And in fact, you can tell the discontinuous interpolating function where this point should belong to. So there is something that's called a marker priority, and that allows you to specify where these points on this boundary belong to. And I'm going to show an example for that. So again, we have the same function as before. We have the mesh element marker union. So we have 0 and 1 is the order of the markers, how they are stored in the finite element mesh. And if I evaluate that function, like I've shown before, at this interface, we get exactly the value of 1. If I now go ahead and recreate an interpolating function and say that the marker priority is 1, 0, so it's just the reverse order. So we say the marker 1 has a precedence over a priority over 0, then we get a discontinuous interpolating function, but now at this value, we get the value of 0. So that's how you define what is going to happen at the interface. So the way to generate discontinuous interpolating functions is by evaluate on mesh, it's number 1, or you can give this an interpolating function as an argument to the discontinuous interpolating function, and it's going to make the transformation itself. So that's how it works basically. We've seen these issues in a few places. They were never that severe, but they came up in electromagnetics. So we've implemented this, and I think we've come up with a good solution. Okay, electromagnetics. This is a completely new field of physics we've started to look at. So we started by adding an electrostatics monograph. We have PD component and boundary conditions. So the function is electrostatics PD component, electric potential condition, electric flux density value. These are the boundary conditions we provide. And this is basically the equation we solve for this electrostatic case. So here's a simple example. We have a micro electromechanical device, and we have a movable top electrode, and this is a bottom electrode. And we want to compute the electric field between these two objects. We create a mesh where we have removed the contacts and set up the variables and parameters. So the variable is now the voltage is what we want. X and Y is a two-dimensional case. Parameters are left 0 for now to illustrate this. Left empty, sorry. And this is what this PD component is going to generate for us. Okay, so we set up some boundary conditions. So we use specific markers again to address boundary conditions. So we have an electric potential where the marker is 1 or 2. So 1 and 2 is the electric potential of 0. So that's the ground, so to speak. And where we have an electric marker of 3, that's the red thing here, we have an electric potential of 20 volts. This is then the solution when you compute it with ND-solve. So it's a new field of physics that we just started to explore. So we have a monograph for this, laminar flow monograph. It explains laminar flow. The function that generates the equations is the fluid flow PD component. It generates compressible Navier-Stokes, incompressible Navier-Stokes. It's useful for non-Newtonian fluid flow and can be coupled with other fields of physics and multiphysics type of things. Okay, a quick revision is compressible Navier-Stokes. So we've got a density, a velocity field U and V, and W in 3D, a convection component, and here we have the viscous stress tensor, pressure, and force. And this is the continuity equation. Yeah, so that's for the compressible Navier-Stokes equation. The viscous stress tensor is the viscosity times the strain rate. This component here disappears in most cases, and the equation will automatically know when to use this and when not to use this. Strain rate is computed by a symmetric gradient of the velocity field. Compressible and incompressible Navier-Stokes. So for the compressible version of the Navier-Stokes, we have a time-dependent density, and the density is actually the dependent variable here. For the incompressible, we already see that this component disappears, and the incompressible is actually a bit harder to solve than the compressible version. Okay, let's look at an example. So we have a lid-driven cavity. That's basically, it's a benchmark problem, famous benchmark problem from fluid dynamics, rectangular region. And we have a wall here, another wall here, another wall here. And on top, we basically have a conveyor belt moving fluid to the right, but not across the fluid, not across this edge here. So we specify a rectangle. We specify the variables, U, V, and P. Those are now the dependent variables, the velocity in the U, the velocity in the V direction, the X and the Y direction velocity, basically. And the pressure is what we're interested in. And the parameter is, we say we'd like a Reynolds number of 1000. And Reynolds number is the relation between the inertial force and the viscous force. And this is then what the fluid flow PD component generates for us. Okay, so let's look at how we solve this. So the first boundary condition, the Dirichlet condition, is actually telling us that U is a fluid flow of 1 and V has a fluid flow velocity of 0 at Y equals 1. So on the top, we have a fluid flow in this direction. The remainder The remaining 3 edges are walls. They have a no-slip condition, so the velocity is 0 everywhere. And we have a pressure point of 0, a reference pressure of 0 down here in this, this corner. So we solve this by ND-solve value, PDE boundary conditions, U, V, and P. And we have to specify a method, and we get to that in a bit. Finite element interpolation order U2, V2, P1, and we'll get to that in a second. And that's going to return us 3 interpolating functions, and we can visualize them. So for example, in stream plot of this, so we see the fluid flow goes to the right. We have a small recirculation area here and another one here. Right, so that's that. So the thing is, if we don't specify this method option, things are not going to work out. The method has failed to compute the next step, and it's not able to solve this problem. And the reason is, if you look at this equation, so we have a pressure here, a pressure here, there's no pressure here in this case. And the way to solve this, simplistically speaking, is that we use U and V, the velocities, and we interpolate them at a higher order. So second order accurate interpolation, and pressure is only first order accurate interpolation. And that setup allows us to solve these type of equations. Again, it's not a Wolfram specific problem. That's a problem that all finite element solvers have. This is what's called a saddle point problem. So what you need to do is you need to specify this these type of parameters here. This is for the stationary problem, and this is for a time-dependent problem, so that you have both cases listed here. Right. In finite element speak, what we do is this is a Taylor-Hood element. Yeah, basically that's how it's called in the finite element world, to specify higher velocity interpolation order than pressure interpolation order. Parameter specification for a fluid flow PD component is to specify either the Reynolds number, we've seen that. You can specify a material like in any of the other PD components, or you specify the actual physical material parameters like dynamic viscosity and mass density. That's how you can specify those. Boundary conditions. So you note that in this case, we use Dirichlet condition for the boundary conditions. And the reason is that because we've only now started adding these PD components for fluid flow, we haven't had a chance yet to make absolutely sure that the boundary condition setup that we'd like to have is valid or works for all type of fluid applications we'll want to do in the future. So think about turbulent flow or things like that. So an inflow condition specifies velocity U or V. Outflow is typically done by specifying a pressure to 0. No slip is a wall condition, so no velocity on a wall. For straight edges, we can have a slip condition, right? And this is a slip condition for a specific straight edge. There is another type of boundary condition we can deal with, and that's very complicated. It's a traction boundary condition, and I'll refer you to the examples in the laminar monograph. So this models this type of boundary condition, and it explains what the reasoning behind that is. Time-dependent problems, again, same thing. You add a t variable here and a t variable here. A fluid flow component, I use glycerol for this example. And here we have a flow around a cylinder, and you see a Kalman vortex sheet behind that cylinder. Non-Newtonian flow. So typically water is a Newtonian flow, but if you think, for example, about ketchup or starch mixtures and things like that, they are non-Newtonian flows. And that means, so if you stir ketchup, it becomes more liquid. So if you shake the ketchup, you can't get it out of the glass. If you stir it, it flows much easier. That's what non-Newtonian flow is, yeah, fluid. Blood is another non-Newtonian fluid. So what we do is basically we approximate the viscosity with this apparent viscosity. Again, like in the hyperelastic materials, we have a collection of non-Newtonian flow models, power law, Kourou, and a few more. Here's a simple example how you'd set it up. So fluid dynamics material model, power law is the law you want to model. You specify the exponent, this n here, minimal shear rate, and all this is explained in the documentation. Here's an example. So we have an inflow on the left, so something's flowing in, and we have an outflow on the right, and the remainder are walls. What we're going to do now is we set up a super simple example, dynamic viscosity 1, mass density goes to 1, and we copy these parameter section over to a power law parameter section, and we add the fluid dynamics material model for the power law with just some numbers. We create two PDE flow components, and we solve them both. And there you see the difference between how a fluid flow, a cross-section of the fluid flow looks at a certain point versus a Newtonian versus a non-Newtonian flow, just to give you an idea of what this is about. Okay, we can also do energy transport. So that means couple fluid flow with heat transfer, and that's typically done via the Boussinesq approximation. So we have a coupling between a heat transfer equation and the fluid flow equation, and that coupling is done via this term, and that's the Boussinesq approximation. Again, theory is explained in the monograph. The example is now we have a rectangular region. We have U, V, and P as for the fluid parameters and the heat parameter T that we want to model. We specify that everything around here is a wall. Then we have a hot temperature down here and the cold temperature up here. And we specify material parameters, and then we solve this. And this is what you get then. So here it's hot down here, it's cold here. And with time, this fluid is gonna start moving just because there's a temperature difference between the bottom and the top. So we've added a Schrödinger equation that models the Schrödinger equation. Again, variables, specification parameters. The default is that it reduces the reduced Planck constant with a mass of 1. That's the same thing. If you do a numeric version of this, you'll get to that same number. That's what the default does. Here's an example of a harmonic oscillator. We have a reduced Planck constant 1, mass 1, Schrödinger potential is an askew potential, and you plug this into an eigensystem, plot the eigenfunctions, that's what you get then. We can do a 2D axis symmetric case. There we have a separation of variables done like this. This is how you set it up. And what we have here is a torus, and we have, this is now the surface we compute on, and from this surface we then can infer the solution in the entire torus. So again, and the eigensystem does the computation for us. And there you see the eigenmodes are in the torus of this equation. Another example is a time-dependent example. So we have a box and we have two slits here, and we have a real and an imaginary part of an initial condition. Set up the Schrödinger equation, find the solution with ND-solve, and then we can look at the scattering of the particle at this boundary with the slits. Probably one of the last things I wanted to mention is a PDE Models best practice. That's a new tutorial where we try to collect best practices for PDE modeling. Whenever we come up with something that we think is useful, smooth step function, how to do that, how to deal with units, infinite domains and things like that. That's how you, that's where you can find some information of how to do these types of modeling.